So next I'd like to introduce Petr Špaček. I can never could pronounce your second name, even though I've worked with you for a number of years, who's going to talk about benchmarking DNS transfers and how completely unlike benchmarking DNS query handling it is. So introduction to Petr.
Thank you very much. Welcome to the talk about weird things which will happen if you try to benchmark zone transfers at a scale. This slide here is just to remind us that the zone transfers are completely different beast than the traditional DNS query response exchange. Obviously, it's multi-step process. We get the optional notify, SOA query response, and then finally the follow-up TCP or maybe even TLS connection to actually transfer the zone content. And the trouble is that this by itself involves a lot of state, and we might have persistent storage on the secondary side, which makes things even more complicated. So the keyword here is a state. That keyword will be with us throughout the talk, and that will cause lots of trouble. Also, for zone transfers, the metrics are very different from the traditional, again, query response. We can look at the zone transfers from the capacity planning angle, or of course the traditional answer latency, but also, for example, a change propagation delay, which becomes important if you offer up your secondary DNS as a service for SLAs. Or maybe you want to scale your secondaries based on the load dynamically, and then it's very important to know how long does it take to bring up a new secondary and get it updated with all the fresh data. And also, at the previous OARC, we've talked about the gotchas in the traditional DNS benchmarking. They all apply here, except that it's much more difficult. Because, again, it's the state. For traditional DNS, we can have echo server and just ping the packets back and forth, easy as that. For zone transfers, it's multi-step process, super complicated compared to the normal DNS. And also, just to monitor the system throughout the process, it becomes a little bit harder because very often the logs and various events are implementation specific. So we have to have different implementations for different servers and so on and so on. In short, it's complicated. And when something is complicated, it's always a good idea to start with a minimal possible example, get things rolling, and then increase the complexity as we go. So with a minimal zone, it should be basically immediate zone transfer done instantly. That's it. Well, let's try. Minimal zone, SOA record, NS record, nothing else. The simplest metric possible, secondary startup time. So we just start the secondary, take the timestamp when we started the server, look into the logs to find out the moment when it transferred the zone, subtract the numbers, that's it. Except that on the first try, we get a negative number. How is that possible? It's like maybe too immediate when the transfer takes negative time. And here the catch is that in case of bind, the statistics channel, which gives you the overview of the system state, actually is using different timestamp precisions for different events. So the server startup timestamp has higher precision than the zone loading timestamp. So if you just subtract them, you end up with negative number. So simple as that, but it can really mess up your measurement. Perhaps minimal zone is too minimal because it's too small. So every imprecision and every tiny noise will mess up the measurement. So let's try with TLD. That's much larger, should average out the noises in the system. We'll see. For that, we are using the CHTLD. Thank you very much for making it publicly available. That's excellent. For testing, we repeat the test 10 times. So we just bring a primary, secondary, wait until it transfers the zone, measure the time. On average, on our test system, doesn't matter what the hardware was about 26.5 seconds, which is reasonably small number, easy to work with. And the differences across 10 measurements were 0.6%. Good. That looks like we have it running. We can maybe rely on it. But again, there are caveats. Basically, the system is so complex that it's necessary to check everything we can. And while going through the logs of these 10 test runs, we've noticed that sometimes the primary take the primary, which doesn't involve any network communication yet. We just started the primary time 0 on the x-axis. On the y-axis, we have a CPU load on the primary. And sometimes it takes longer time to start the primary. And sometimes the primary is not using 100% CPU, even though it should, because it's just loading the data. I mean, there should be no limit. Well, I will spare you the drama. Fast forward through the investigation. Turns out that the Linux kernel does provide lots of monitoring interfaces. One of them is called pressure stall information, and that's an interface throughout the kernel can tell you this process is being stalled by some resource. In this case, the chart is, again, x-axis is time since we started the server. On the y-axis, we have percentage of time where the process was waiting for input and output. So in this specific case, 1 run out of 10 was being stalled by I/O. So that's kind of unusual for DNS because you don't see that with the normal query response exchange. But as soon as you get to the large zones, the I/O and the latency involved by the storage subsystem can really mess up the measurement again. So the takeaway is, for zone transfers in the real operations, you have to take into account state of the storage subsystem. Okay, another source of noise, let's get rid of it. Let's say that we've eliminated the impact of the file system caches and we measure again. X-axis, time since we started the secondary server, y-axis, CPU load on the secondary server, and we have 4 measurements, 10 times each configuration, so 40 measurements altogether, and we compare the plain TCP with TSIG, and then DNS over TLS zone transfer without TSIG and with TSIG, these 4 configurations. You can see for yourself the CPU utilization is very close, very similar to all of them. And if we take the time it takes to transfer the one TLD zone, the CH, and normalize it so that plain TCP is 100%, we can see that the plain TCP and transfer over a DNS over TLS is actually on average the same time. So basically it costs almost nothing, almost. At the same time, to my surprise, the measurements show that the TSIG is way more expensive than DNS over TLS. That's what the measurement says. It seems that we finally got the system running. We have something nice. We can be happy that we can measure stuff. So let's try some different use case. For example, the typical hosting setup. You have lots of customers, and vast majority of them have basically SOA, NS, wildcard. That's mostly it for most of the small zones. So we try different numbers of the zones on the secondary and primary. And again, because we don't have time for anything more complicated, we focus on the secondary startup time. And we start with a clean slate. The secondary have only config file, nothing else. So it has to download all the zones from scratch. And the theory says that the time it takes to start up the secondary should linearly increase with the number of zones configured, because all the zones are the same, so it should be linear. And the impact of different transport options like TCP or DNS over TLS and so on should be basically the same as we have seen for TLD, because, I mean, why not? And this is the summary slide, which sums up the measurements for each number of zones. We've repeated the test case 10 times. That's the vertical axis. And on the horizontal axis, we have average time to transfer a single zone. So the total time it took to start a secondary was normalized to the number of zones. So in theory, all the bars should have the same length. Because again, if it's linear, it doesn't depend on the number of zones. All the blue bars should have the same length, which is most definitely not what's happening here. And what's even worse is the red stripe, which indicates the error bars between the minimum and maximum time it took to start a secondary. And that's just like insane. There's no other word to describe it. So what is going on? Quite obviously, the 30,000 zones, for some reason, it's a magical number. and it's the slowest of them all, so we will focus on that one. Again, these slides are kind of showing the results of the investigation. It had like lots and lots of dead ends and trying to find out what's going on and why it's behaving in such weird ways. So, but let's say that we were inspired, okay, it is being slow, we will look at the CPU load. And this is on x-axis. Time 0 is the moment where we started a secondary. Y-axis is the CPU utilization on secondary. You can see that it goes over 100%. 100% is 1 CPU. 400 is like 4 CPUs on the machine. So the secondary went up, consumed like your utilized 3 CPUs for a brief moment, and then it went down. And before I continue, let me clarify one thing. The blue line is the average across 10 test runs, and the background is the range between minimum and maximum value across the 10 test runs. So you can see that the CPU utilization wildly changes over time across the 10 test runs, but it starts with a spike, and then it's only going down and down and down until at around 66 seconds it hits 0. Basically, the CPU is not doing anything. And at that point, 2 out of 10 test runs finished all the 30,000 zone transfers and were like ready to serve clients. In remaining 8 out of 10 test runs, for mysterious reasons, it took 2 more minutes to finish the zone transfers. Why? And this is exactly the point where this keyword state came back for us. Eventually, we looked into the logs on the secondary servers, and all of them, for all the test runs, started logging around roughly the same time, error message, failed to connect, address not available, which doesn't really make a sense because everything was configured statically. We were not changing anything on the network side. The kernel didn't log anything about link going away or anything like that, but that's what the logs said. And turns out that this is not about the address, but about the ports. The TCP ports have TCP has its own state machine, and the ports go through lots of different states. At the end of the connection, when everything is closed down, the TCP socket reaches so-called time wait state, where we are basically waiting for like all duplicated packets to come through so they can be thrown away safely. And again, Linux kernel has lots of monitoring interfaces. One of them shows a number of TCP sockets in a so-called time wait state. And we can see that at the beginning of the measurement, it goes sharply up, then it slows down, starts dropping, and at that point, 2 out of the 10 servers finish all the zone transfers, and the remaining 8 test runs take 2 more minutes. Why? Well, it's really complicated. And simple at the same time, which is really fun, because the TCP connection is basically 4 tuple. It's a combination of source IP address, source port on one end, and destination IP address and destination port on the other end. And when we want to open a TCP connection, by default, the operating system goes and picks a random number from so-called ephemeral port range. And by default, on the test machines we are using, there were like about 28,000 ephemeral ports. And after the connection is finished and closed, it reaches the time wait state, and it's stuck in that state for roughly 1 minute, at least on our test machines. So with that information, we will investigate again the same chart, but we include more information. Here, the box on the left side is time range when across the 10 test runs, the secondary logged the message that they have transferred the 14,115 zones, which is exactly half of the ephemeral port range. And we can see that this is pretty fast. In first 10 seconds, they transfer like 14,000 zones. Then it slows down. We don't know why, but it slows down, and it takes like more than twice that much time to consume the other half of the ephemeral port range. Then it starts logging that address is not available with quite wide time range. And then it starts dropping, and we've discussed that before. So what is going on? If we overlay the same events over the CPU load, we can see that, yes, at the beginning, there is a spike, then it slows down, then everything goes to 0. And one explanation why it takes so long time is that by default, bind built-in retry timer is 30 and 90 seconds. So if it fails the transfer, it will try in half a minute and then in 90 seconds again. So that explains the long period where nothing happens, seemingly. OK, so but why the CPU consumption? If you look at the CPU profile, we'll find out that basically 64% of CPU time was completely wasted in bind syscall, which basically means that the secondary server is looking for the empty port number, but it's not finding it. So it's just looping and looping and looping, and it's just crazy. The reasons for that are complicated. I mean, you don't have time for it, so I will just refer to this excellent talk. If you ever do TCP at scale, recommended watching. But we want to verify our hypothesis that actually the TCP time wait state is the source of the problem. So again, we dive into the Linux kernel docs. We find this wonderful configuration command, which documentation says that you must not ever use, but we are in lab and we just want to confirm that we are on the right track. So basically, we configure the operating system to limit the number of TCP sockets in the time wait state to just 1,000, so like much lower number than the ephemeral port range, and then repeat the test. And this is what we arrive at. The blue line is the original measurement. That's what you have already seen. The orange one is the one with the number of sockets limited to just 1,000. And we can see that everything is much faster. The CPU utilization at the beginning is the same, but then basically in like about 10 to 15 seconds, all the transfers are done, 30,000 in one go. And that confirms that actually the time wait state is the source of the problem, which is like slowing down the system. So yeah, that's nice in lab, but maybe not practical. But at least we've confirmed the behavior of the plain TCP. We now can see that, OK, we understand why it was slow. Now the question becomes, how does it translate to the DNS over TLS? In theory, DNS over TLS is using TCP, right? So it has to be suffering from the same problem, because like by definition, it's the same transport. Except that's not what the measurement data show. The blue bars are the same. You have seen the data. The orange bars are from the measurement with same setup, except that we were using DNS over TLS with a TSIG. And you can see that the length of the orange bars is like roughly the same. They are not like so wildly all over the place as the blue ones. So basically, the DNS over TLS is behaving as we originally expected at the beginning, where the time to transfer the zone doesn't really depend on the number of zones. That's what we wanted, but we didn't get it for TCP. But how come it works like that for DNS over TLS? And it's basically cheating. First, as currently implemented, bind doesn't do the first SOA query for DNS over TLS transfers, but that's not a factor. If we eliminate that, that's like just UDP query going, and that doesn't really affect the TCP state. So that's not it. But there is a catch. If you establish a TLS connection, it's a pipe over TLS, and at the end of the TLS connection, the protocol says that you are to inform the remote end and send a message called TLS close notify, basically saying inside the TLS, by sending the data over the connection, we are ending the connection, go away. And the other side is supposed to respond with the same message, TLS close notify, and basically confirm inside the TLS tunnel that yes, we are closing the connection. That's what bind does, except one catch. The zone transfer client actually sends the notify message out to the remote end and then immediately tears down the TCP connection. So it's not waiting for the response from the remote end. But the remote side doesn't know that, right? So the remote side like dutifully complies and sends the close notify message over TCP, but it sends the message to the closed TCP socket. So it gets delivered to the operating system, and the operating system is confused and says, well, this socket is already closed. I don't know what to do. And instead sends back a TCP reset, and basically it resets the state of the TCP stack for that particular socket, and that gets us out of the time wait jail. So quite accidentally, DNS over TLS is much faster if you do lots of zone transfers. The takeaway is basically don't trust anything at all. If you think that something will behave linearly in DNS, you need to think again until you change your mind, because it's definitely not linear in any aspect I ever looked at. And we are up for questions. Thank you very much for your attention.
So actually, there is a question. There was a bit of confusion over who was monitoring the questions in the channel. There is a question from Hazel, who is another PC member, who says, when you say the red error bars represent the difference between the min and the max, had you considered doing a box and whisker plot instead, showing the different quartiles?
Yeah,
and there's a bunch of other things about faceted scatter plots and other type feedback.
I mean, the only point I was trying to make is that it was complete mess, and delving into the specifics of the mess wouldn't bring much more information.
Jeroen Bulten, SIDN. Very interesting presentation, by the way. You did a bit of TCP tweaking to improve on the zone transfers. Have you considered changing the algorithm that Linux? I assume you were doing your tests on Linux, but you have, I believe, the standard algorithm is cubic. There's also Reno, BBR by Google. Have you considered doing tests with different algorithms?
If I understand the question, you mean the congestion control algorithm?
Yes, exactly. Right? Yeah.
To best of my knowledge, they don't affect how the port number is assigned.
That is correct, but they could affect the throughput when you are transferring large zones, for instance.
Yes, but in this specific test, it was minimal zone, so it fits into one message. So it doesn't have any impact.
Okay, thank you.
Yeah, it's Tamás, PCH. You were doing your measurements with one host, basically, right? I mean, one secondary.
Yes, it was between single, primary, secondary. The simplest possible setup. It was just to illustrate that it's so messy that you can
my only question is that would you be interested to maybe redo the test with maybe more secondaries? 1, 2, 5?
Yeah, sure. I mean,
100?
It has infinite amount of variables. So, I mean, the trouble is basically picking up your target and then sticking to it, because, I mean, in 20 minutes, we cannot really go into much more detail.
Thanks.
Yeah, but I'm happy to discuss, of course. Catch me.
Thank you very much.
Thank you.